Hello and a warm welcome to this Teledyne E2V webinar in cooperation with EE Times. My name's Mark Holdaway, and over the next 45 minutes I'll be covering a topic that I think many of you are curious to learn more about. This is about the latest developments in software-defined radios. The headline says it all, namely that direct digital conversion in the Ka band is now within reach of the latest data converters. So who's this for? This high-level session has been designed for engineers with a general interest in software-defined radio, or those simply wanting to stay informed of the latest leading-edge radio technologies. In this session, I'll introduce you to SDM, that's Software-Defined Microwave Systems, and cover the design efforts happening today at Teledyne E2V to extend digitization all the way into the microwave K band, and in fact including the Ka band, which is from 26 to 40 gigahertz. It's a change likely to impact microwave radio distribution infrastructure with major implications for a range of high-end applications, including satellite communications. Let me take a few moments to review the agenda. Firstly, we'll look at some of the key industry trends and applications for Ka band usage. I will then introduce RF Softwarization, which lies at the heart of software-defined microwave technologies. Then I'll briefly cover some of the technology challenges faced by developers of microwave radio systems today, before taking a brief look at how both the receive and transmit signal paths are being innovated. In particular, I'll introduce a four-stage product roadmap destined to yield the industry's first Ka band SDM solution. Without doubt, the biggest single reason for the increasing interest in Ka band operation is the ever-advancing demand for data consumption on the move. In a 2018 report referenced here from market analysts at IDC, they predicted a compound annual growth rate of 61% in data growth to the mid-decade, with an annual demand hitting 175 zettabytes by then. It is challenging to grapple with such astonishingly large figures. If you're confused by data magnitudes, i.e. you're not clear how large a zettabyte is, well, in tech speak, a zettabyte is 10 to the 21 bytes or a billion terabytes. In addition to this burgeoning data market, we're currently seeing much expanded interest in so-called new space. That's a term coined in a recent European Investment Bank report into the space industry that highlights the growth opportunities. Space is clearly benefiting from a resurgence in interest as it sees both venture capital funds and private entrepreneurial interest. Few could have missed the SpaceX, Starlink and Amazon plans for low Earth orbit, space-based internet infrastructure, for example, over the last couple of years. Beyond the commercial concepts mentioned previously, other applications include high-throughput satellites, low Earth orbit and CubeSats. Satellites will no doubt be providing 5G backhaul services in the immediate future. Moreover, SDM technologies will find a rapid home in electronic warfare and electronic countermeasure systems. Finally, high-resolution synthetic aperture radar systems are being used to significantly improve the capabilities of Earth observation systems and the science associated with them. What's special about Ka band? Probably the most important benefit are the wide bandwidth signals it supports. Ka bandwidths are double that of Ku band and 5 times that of C band. It's true Ka band is more susceptible to attenuation from airborne water droplets, but the space industry has already devised a multiplicity of solutions to this problem. One example includes ground station diversity, another exploits power and modulation schemes. With the substantially increased bandwidth, another benefit is throughput rate. This partly arises from raw bandwidth considerations, but equally the Ka band systems produce smaller spot beams, meaning inherently increased frequency reuse within a geographical footprint of a given satellite becomes possible. Finally, with smaller wavelength signals, the physical size of key components such as antennas falls, helping to improve the all-important swap or size, weight and power performance of a given design. I now want to dig into RF Softwarization. This lies at the heart of so-called SDM or software-defined microwave systems. I'm sure you're already familiar with the concept of Nyquist sampling theorem. This rather simplified radio structure is the traditional supraheterodyne receive circuit. The RF signal is fed into the RF bandpass filter on the left before being mixed at the intermediate frequency stage. Post-IF, a second bandpass anti-alias filter is required ahead of the baseband ADC. The mixer performs a frequency translation, down-converting the band-limited RF signal to a frequency that falls into the baseband range of the ADC. This is a system that has predominated pretty much every class of software and digitally assisted radio system over the last few decades. It works well, but suffers from considerable analog circuit complexity in the signal chain and provides a very restricted range of programmable options. Furthermore, it's heavily determined by the hardware characteristics. A modern SDM exploits wideband data converters and therefore pushes the converter increasingly closer to the source RF signals. You'll note that in this case, the local oscillator and IF stage have gone, and now the ADC samples directly from the RF bandpass filter. Sampled signal power is aliased into the sample rate range of the ADC. All other frequency operations are now handled applying a digital signal processor in the digital domain. SDMs are getting increasingly advanced as raw processing power has helped here significantly. Furthermore, ultra-wideband ADCs are now more widely available. Here are a couple of example ADCs, both of which feature an analog bandwidth in excess of 4 GHz. On the left, the AD550 is a dual-channel design capable of sampling at 1.6 gigasamples per second, or up to twice that, 3.2 gigasamples per second, in time interleaved mode. The AQ600, with 4 cores, can sample double that again and offers an expanded analog bandwidth up to 150% that of the AD550. When evaluating the suitability of data converters for use in a specific wideband RF application, it's often helpful to consider the SDM boundary planning guide shown here. The standard microwave frequency bands are plotted along the ordinate and the class of SDM along the abscissa. Clearly, a Class 1 baseband ADC has no access to microwave RF energy without the aid of a supraheterodyne frequency translation stage. The SDM boundary marks the separation of the analog from the digital radio domains. The upper left-hand corner of this chart is the analog radio zone, whilst the lower blue zone identifies the digital radio domain. Moving along the abscissa, higher class ADCs extend digital reach and indicate the potential for more agile radio systems. By the time you have a Class 5 ADC, it is possible to implement an SDM that can directly access the C-band. This chart is useful to plot ADC dynamic characteristics in each of the ordinate frequency bands to assess if a target ADC meets the designed requirements. In this chart, I will plot the performance of the two ADCs introduced earlier. Both ADCs can partially meet Class 5 C-band requirements. The first, the EV12AD550B, has a peak bandwidth of 4.3 GHz, which just makes it into the C-band. 3 input frequencies are shown here with the associated spurious free dynamic range statistics. The second device is the newest part, the EV12AQ600. It features nearly 150% more bandwidth, best exemplified by the fact that it delivers 67 dB SFDR at 5.6 GHz. Unsurprisingly, with its higher bandwidth, the AQ600 would make the superior choice for the C-band applications. However, the AD550 might be the better choice for L and S-band operation. Concluding this RF Softwarization introduction, I want to emphasize once again that the boundary between the analog and digital domains is being pushed increasingly into the realms of RF as shown by the lower block diagram, with the ADC clearly migrating towards the antenna. Two factors support this move. Firstly, the availability of significantly faster signal processors, and secondly, the availability of some pioneering ultra-wideband data converters. Eliminating the need for IF stages and their local oscillators, radio design simplifies, and it is then possible to perform all the frequency domain processing in the digital domain alone. That means increased versatility for future air interface systems, as well as reconfigurability and enhanced frequency reuse. So before going into some practical products, let's just consider briefly the technology challenges that are upsetting current signal path innovation. The chart on the right highlights a problem with Moore's law that has emerged over the last few years. Although semiconductor device scaling continues, leading to increased transistor densities, analog and mixed signal circuits have started to suffer a performance decline. In fact, we reached a critical node some years back, hitting the 28 nanometer gate length, as you can clearly see here. The chart shows that finer bulk CMOS geometries are no longer providing a speed advantage for mixed signal circuits, effectively. Moreover, in this second chart that documents analysis by researchers at IBS, you can see that product development costs are accelerating with each diminishing process node. We've reached an inflection point today where bulk CMOS is prohibitively expensive for all bar mass volume markets. Modern ASICs based on bulk CMOS no longer work for engineers, no longer help them eke out ever more bandwidth. It's a problem demanding alternative options. This is a key point we will return to again shortly. The first point of focus is the receive path. At Teledyne E2V, foundational research has been ongoing now for several years to improve the ADC input signal bandwidth. One solution to extending ADC performance has already been hinted at, namely the use of time interleaving of multiple cores. However, that does not expand signal bandwidth. Approximately 2 years ago, Teledyne E2V established a three-pronged strategy to expand bandwidth as follows. Step 1 was to establish a proof of concept sampling system pairing a 20 GHz plus track and hold amplifier with the existing AQ600. The target of this work was to validate whether the track and hold and ADC combination could achieve viable spurious free dynamic ranges beyond the raw bandwidth of the ADC. Step 2, given success in the first step, was to work to further extend the bandwidth of the microwave sampler and double ADC sample rate to 12 gigasamples per second, supporting a 6 GHz wide channel. Step 3, take the learnings of the first two steps to produce a true integrated Ka band quantizer and commit to a silicon development. As you'll soon see, we are well into the third step of this plan. As further introduction to this segment, I want to highlight that for a sampling solution to work into the Ku or even the Ka band, there's still a significant frequency enhancement needed. Today's widest bandwidth solution is the EV12 AQ600, which can provide direct access into the C band as we've seen previously. However, the K bands sit at between 3 to 6 times higher frequency in the spectrum. So how is this rather significant gap to be bridged? Using off-the-shelf components, an experimental test circuit was conceived, which enabled frequency translation or down conversion from around 20 GHz using a track and hold circuit. The resulting module included clock management to ensure sample clocks of the track and hold amplifier and ADC were synchronized. The graphic in the center of this screen shows the modular elements of the experimental circuit. On the left-hand side is the RTH120, and the ADC is shown on the right. The dual sample track and hold circuit provides a hold time that extends beyond half the sample clock period. And as stated here, it has a bandwidth in the order of 24 GHz. The EV12AQ600, as previously mentioned, is a 12-bit converter with 1.5 gigasample quad cores, which has a bandwidth and input sample bandwidth of 6.5 GHz. The core has been designed specifically to support time interleaving of all 4 channels. This chart plots the frequency response of the track and hold amplifier at 3 different input signal levels. And as you can see, response peaks out to about 24 gigahertz. This is a plot of the first spurious-free dynamic range tests that were carried out with the experimental board, and they look fairly promising. But one thing stands out, and that is quite a significant variation in performance dependent on the input signal level. And in fact, that characteristic was a great signal of some steps to take to improve the overall performance of this experiment. 3 major findings resulted from the original experiment as follows. Firstly, input signal power clearly affected the performance of the track and hold amplifier, with second harmonic distortion being particularly noticeable. This suggests that the selection of input signal levels was crucial to optimizing the track and hold's functionality. Alone, this could yield a 10 dB lift in dynamic performance. Furthermore, there was noticeable fall in dynamic range at an FC/4 rate, i.e. at a quarter the sample clock rate. That's a telltale sign of a problem with the time interleaving within the ADC cores. It was not especially surprising since the ILG is calibrated during production tests and optimized for baseband frequencies. Further work indicated a 15 dB lift in spurious-free dynamic range was possible using a high-frequency calibration. The final observation was tied to the integral nonlinearity performance of the ADC. This also had a marginal impact on dynamic range. Again, establishing a high-frequency calibration point saw product engineers achieve a further 3 dB SFDR lift by the end of the experimental work. The optimal high-frequency calibration that was ultimately used for this experiment was 21 gigahertz. In the second phase of this project, a more refined design approach was used. The resulting PS640 prototype included a pair of time-interleaved AQ600s, doubling the effective sample rate, now at 12 gigasamples per second. This sampling block was then tuned with a new experimental microwave sampler targeting a 30 gigahertz bandwidth. This prototype, though not intended for production release, adopted a more systematic design methodology. Firstly, a new high-frequency substrate material was identified, and multi-chip techniques were used to minimize parasitic component effects. Gone are any wire bonds in favor of shortest path bump die connections. Moreover, to ensure optimum dynamic performance, a full high-frequency electromagnetic study was commissioned, as illustrated here, to ensure matched impedances throughout, and that a highly functional and quiet design resulted. Furthermore, considerable effort was needed to achieve a good calibration balance between the discrete ADC pair, given their physical separation on the substrate. The resulting system in package is also pictured here. This plot speaks for the improvements made possible in this second development phase. Here, a 25 gigahertz tone is sampled at 10 gigasamples per second and yields a useful spurious-free dynamic range of 50 dBc. In the final stage of this receive path expansion development, the company plans to develop grounds up a new Ka-band solution. The current development envisions a 12 gigasamples per second single channel broadband ADC with high frequency optimized interleaved cores. Its front-end quantizer will exploit all the lessons learned by the company over the last few years to stretch input bandwidth out to 40 gigahertz. Whilst the company remains tight-lipped on specific dynamic performances of this system-in-package solution, it is to be expected it will achieve over 50 dB spurious-free dynamic range across most of the Ka band. The device will again use multi-chip module assembly techniques and reach end customers in as a system in package solution. It'll feature a modest 20mm square LAN pattern. In helping customers achieve the goal of flexible SDM applications, this design also offers several simplifying design features, including the adoption of single-ended signal input and clock lines, the inclusion of their license-free Easy Stream high-speed serial data link technology. There's an onboard digital down conversion module. There's also the availability of the unique sync chain feature that ensures deterministic multi-channel array sampling, which is of significant help to users interested in deploying beam steering techniques. This table once again maps out the 3 development steps used in the receive path. Over the course of these efforts, it's been anticipated sample bandwidth 20 GHz of the experimental demonstrator to the upper end of the Ka band at 40 GHz. And so far the results reflect this ability. Now we'll turn to the other end of the signal chain. This is the transmit path, and we'll look at some of the recent digital to analog converter developments. This block diagram shows the dual channel data converter, the EV12 DD700. As you can see, there's quite a lot of functionality on this chip beyond the bare bones DAC. So, as previously mentioned, this is a 12 gigasample per second dual channel feature-rich product. It features a 25 gigahertz bandwidth. It has the low latency Easy Stream serial data interfaces. It provides analog output power mode control, a complex dual 32-bit numerically controlled oscillator, and as you can see here, a number of significant digital processing features. I'm showing here the output power plot for the 3 different output modes provided by the chip. The red trace is the standard non-return to zero output, which essentially optimizes power projection in the first and second Nyquist zones. The blue trace, dotted trace, is the RF trace, which essentially optimizes output power in the X band, as you can see here, roughly between about 8 and 14 gigahertz. And then finally, a new mode with this particular DAC is the twice RF mode, which, as you see, optimizes power projection primarily into the K band, shown here from around about 18 to 26 gigahertz. There's a lot of digital processing included on chip with the DD700, as this block diagram of one channel indicates. Stepping through the primary digital functions, there are 5 blocks as follows. The DUC, or digital up converter, comprises various delay stages, interpolation stages, gain, and a 32-bit numerically controlled oscillator. A second block is the direct digital synthesis block that allows for local frequency generation, essentially eliminating the need for continuous data streaming from a separate DSP block to the DAC. Fast frequency hopping is now shown. Beamforming is a complex function supported by this particular DAC. It's aided by the provision of gain and phase control stages within the digital up converter, as shown here. Finally, there's a chirp control block designed to generate characteristic signal signatures used in typical radar applications. I'd like to take the opportunity to show you a few live plots. The first one is a single tone. As you'll see here, the fundamental is projected at 20.15 gigahertz, and over on the right hand side you'll see the first spectral spur labeled D2, which is roughly speaking 50 dB down on the fundamental. The next signal to show you is a 2 gigahertz chirp signal operating between 6.5 and 8.5 gigahertz. So the final live plot for this seminar is an example of the DAC operating in frequency hopping mode. This has been slowed considerably. What you'll see here is operation in the second Nyquist zone, switching between 6, 9, 7 and 8 gigahertz. In reality, the part can switch frequency rapidly as quickly as sub 10 nanoseconds. This final output characteristic shows a typical multi-tone signal. The signal captured is in the range 20 to 25 gigahertz with a 500 megahertz per division time base. The signal bandwidth is 2.26 gigahertz, starting at 22.4 gigahertz. The DAC is sampling at a 20 gigahertz clock with the twice RF output mode and the inverse sync filter enabled. Moving away from core semiconductor technology momentarily, I want to highlight a package technology being scaled up today at Teledyne E2V. I want to highlight a new package trend. It's one being scaled up rapidly today at Teledyne E2V. System in Package, or SIP, offer a modern alternative integration approach. We saw earlier how bulk CMOS technology no longer supports expanding bandwidth needs. That's because FMAX has collapsed. This is forcing a natural disintegration of analog and mixed signal functions away from bulk digital CMOS, as alternative process options become increasingly mandatory for RF functions. In the diagram, moving from RF input on the left through to the FPGA, you'll notice that three separate monolithic die and silicon technologies are identified. These are BiCMOS, RF CMOS for the ADC, and finally digital CMOS for the FPGA. The mixed signal aspects of this subsystem are delineated by the dashed green line. SIP assembly brings three singulated die together, packaging them bumped and flipped onto a special high-frequency substrate. The substrates often encapsulated to enhance thermal performance and provide extra environmental protection. Whilst lacking the optimal form factor of an SoC approach, system on chip approach I should say, SIPs still provide a micro-miniature integration route, allowing a cost-optimal selection of silicon processes for key functions. Furthermore, SIPs offer tailor-made designs, not dissimilar to giving a customer flexibility as found with traditional ASIC choices, for example. In readying SIP technology for market, our customers often raise concerns about SIP's durability and ruggedness. Teledyne E2V have already qualified SIPs to meet the toughest environmental demands, including up to QML-V and QML-Y level for space applications. Equally, you may doubt their mass production scalability. Rest assured, however, such worries are unfounded given that many mobile phone modules have exploited SIPs for over a decade now. Looking further out, the introduction of optical photonics offer an even more exciting future prospect. Over the last few years, the Optical Internetworking Forum have produced a series of proposals for optical serial data links running between 6 and 56 gigabits per second. SIPs provide an ideal path to introduce such high-performance signaling in package. As this graphic suggests, this approach opens up the prospect of fully distributed SDM architectures. The final future prediction in this session is the arrival of Softsats. Softsats are a new class of agile SDM-based satellite platform that make the most of the implicit flexibility of SDM air interfaces. They will feature over-the-air reconfigurability and programmability. They may use electronically steerable antenna arrays for additional versatility. These versatile space-borne platforms will facilitate multi-mission payloads and help share investment costs across a multitude of customers and applications. It's even possible that SATCOMs as a service may emerge during this coming decade as a result. So that almost concludes this quick tour of the latest SDM technologies, and I thank you for your sustained attention. Hopefully today you have a better understanding of state-of-the-art data converter capabilities and a feel for the pace of advancement in the world of SDM radios. Ka-band radios are widely viewed as the future of space communications, and as such will form the critical backbone infrastructure of our future data networks. The flexibility such radios offer looks set to cause a major paradigm shift in future air interfaces. So before closing, I'd like to take the opportunity to recap on a couple of the key points. After a brief introduction to RF softwarization, I introduced the SDM boundary mapping tool. This useful tool allows for assessing the capabilities of data converters addressing specific design needs of individual microwave signal bands. In reviewing this, we looked at currently available devices, highlighting the classes in which they fit. Existing ADCs covered here included Teledyne E2V's Class 4, EV12 AD550 and Class 5 AQ600, both of which have been introduced in the last couple of years. With the arrival of the PS640 development work completed this year, Teledyne now has a prototype Class 7 solution ready. The announcement of the development of the full Ka-band quantizer solution, also introduced today, together with the dual DAC, leads the company to having a Class 8 solution for the receive path ready by the end of 2021. Roughly speaking, that's a development time of little more than 5 years and an astonishing rate of advancement to SDM technology. I hope this brief presentation has been thought-provoking. During the course of this session, we touched upon the trends driving growing interest in Ka-band microwave communication link technology, specifically an explosion in data demand and interest in future new space opportunities. RF softwarization was then covered and what it means to radio system design, including the fact that data converters are increasingly displacing complex analog radio circuits. The design challenges, principally the collapse in Fmax performance beyond 28 nanometer CMOS process nodes. This suggests the need for a new mixed signal circuit integration paradigm, and we propose system-in-package solutions for that. A quick review of the three-step receive path development project within Teledyne E2V, followed by a look at the K-band DAC, the EV12 DD700, the first in its class to integrate feature-rich digital functionality to ease agile SDM transmission paths. And then a close on the points that a Class 8 quantizer is in development now, which will finally bring over-the-air reconfigurability and reuse, whilst enhancing system swap benefits. That's the size, weight, and power of the system design. As hinted at earlier, once a Class 8 SDM solution exists, full Ka-band soft radio design will likely herald an unprecedented bout of air interface innovation. In space, we anticipate seeing the first software-defined satellite communication platforms emerge and go on orbit mid-decade. Furthermore, these platforms will offer a new price point for data communications infrastructure. Satellite platforms will likely become more standardized and multi-mission capable, meaning infrastructure costs are shared across customers and applications, improving return on investment. The versatility of this technology arises from the following considerations: over-the-air reprogramming and reconfiguration, frequency reuse, essentially ultimate flexibility, optimum mission-defined signal path operation, and finally, and possibly most importantly, increased swap, as in improved size, weight, and power performance. Finally, I want to let you know of a few interesting resources provided by Teledyne E2V online and detailed here. Of particular interest are resources explaining the unique deterministic synchronization technology embedded within Teledyne E2V's data converters that insist in building and implementing multi-channel phased array capabilities. There's even a short and informative demonstration video. Other resources include a variety of tech notes and white papers. Finally, I'd like to highlight the main web address shown here on the slide bottom left.
On behalf of Teledyne E2V and EE Times, I'd like to thank you for your interest in our ongoing RF softwarization initiative and advancing SDM technology. To get the very latest information and updates, including potential access to confidential technical documents, feel free to either contact the factory directly or get in touch with your local technical representatives. Thank you very much.